Hello, my name is Alex, and today I'll be telling you about a project that I've been developing within SpECTRE under the mentorship of Professor Niels Deppie. It's a project that I have now, it's something that enables you to write tensor equations more easily in C++ code, and it's something that I have now made fast enough for us to use in production in SpECTRE. So SpECTRE is our open source numerical relativity code. It lets us do really exciting physics already. But in order for it to do that exciting physics, we need to code up lots of physics tensor equations as C++ code. And this is an ongoing process for us to do the science that we do. The thing is that coding up these equations is often a very tedious and time-consuming process. It's prone to human error. And so what would be nice is if we could make this process easier and more foolproof. The usual way of implementing a tensor equation in code is with a set of for loops like you see here. This is an example straight from SpECTRE. And this isn't too bad to write, but it does take some care and it's easy to make a mistake. And it would be nice if instead we could just write something that's familiar to us, that looks like the notation that we're used to, that looks like the equation. And that's exactly what SpECTRE's tensor expressions already allow you to do. So down at the bottom, you can write that one-liner and it will do the work of the for loops above it behind the scenes for you, and you don't have to worry about it. All you have to do is write your tensors and in parentheses supply your upper and lower indices, and it will do the magic for you. Now maybe writing one set of for loops isn't so bad if you think about that, but here's some code in SpECTRE where we have 4 of these kinds of equations back to back, and you can see this gets tedious very quickly. And if you write these equations instead with tensor expressions, you can see that you save the developer a lot of keystrokes and a lot of time and headaches. Also, we implement these big scary equations up here to evolve our curved spacetime, and writing the for loops for this is not fun. It can get very complicated. There's a lot of room for error, and it's nice to be able to write these intuitively instead. Another feature that tensor expressions provides us is, or in SpECTRE, is it will do compile time checks for you on your math. And so if you were to write an equation where you, on accident, repeated an index or didn't balance your free indices on the left and right-hand side, the compiler will catch it for you, as opposed to, say, running a simulation for a couple weeks and then getting data that was computed incorrectly and being sad when all you did is make it a small typo that basically anyone could have made. It's a very easy mistake to make. One other feature that these tensor expressions provide that's new that we'd like to highlight is that it also allows you to specify if you would only like to refer to the spatial components or the time component of a spacetime index. So in this example, G is the spacetime metric, and using the suffix I, J, or K on that first argument indicates the tensor expressions. I only want the spatial components, and the suffix T indicates I just want the time component. Okay, so we have tensor expressions. There's lots of benefits. We're excited about them. But the thing is, we can't use them unless they're fast enough. There's no sense in using them instead of the for loops if they're going to slow down our simulations that already take us a lot of time. And so what I needed to do to be able to make sure that we could use these in production is I needed to time them. So I picked a set of equations that are representative of the kinds of equations that we see in our SpECTRE code. I implemented these equations with loops, and I also wrote them with tensor expressions. I timed them, and then I compared the times. Pretty simple. Up here I have some problem cases, but in general, tensor expressions performed very well compared to the loops. In general, they were slightly faster than the loops or on par with them. But in these 2 examples on the screen, they were egregiously slower, and that was a problem. These cases were when our tensor components were vectors of doubles, which is how we represent tensor fields. So this first case was a contraction over 4 indices, and it was 200 times slower with tensor expressions than loops, which is horrible. And the second example is this dt pi quantity, which is this massive equation with lots of operations, and it was 9.5 times slower with the tensor expressions than with the loops. And this needed to be addressed. If we want to use them, this needs to be fixed. And so in order to address this, I had to ask myself, okay, when I see an equation like this, what operations are actually happening? How are the loops computing this equation? And how are tensor expressions computing it differently? And so if we look at this expression, what's really happening is 256 products being summed, which is a lot of operations. And when you implement this as loops, what you essentially are doing is just doing one product at a time and accumulating. So you do one product, add it to the result, do the next product, add it to the result. You do that 256 times. Now, tensor expressions does things differently. It computes the equations as one massive one-line, or in this case, it'll be massive, but it'll compute the equations as one-liners. And so in this case, it's one massive one-liner of all of those products being summed. And when I dug into this, what I found was that if I were to sum only a few products in one line, which is this part of the graph where orange is below the blue, if I just sum a few products in one line, the one-liner was faster than doing one product at a time. However, past a point and beyond, the one-liner was a lot slower. So when you get to 2 to the 8, 256 products being summed in one line, that one-liner was 100 times slower than just doing them one at a time, which is a big difference. And this intersection of the lines suggests that maybe there is some optimal size of expression where if we do a certain number of operations at once in one line, that can be the fastest way for us to compute this, and we can speed tensor expressions up. And so what I next looked at was okay, so instead of just doing one product at a time, what if we consider now trying doing 2 products in one line, or 4 products in one line, or 8, and so forth. And when I looked at that, I found that if I did 4 products being summed in one line, that was the fastest way to compute this whole 256 products being summed. And I will note that 4 of these is 8 total operations, and when I benchmarked vector addition, 8 vector additions was also happened to be the fastest way to do addition. And so what idea this gave me was, okay, so what if someone types this equation that has lots of operations, can we automatically cut it up into smaller pieces of size, 8 operations at a time to make it compute the equation faster than it was before when it was just this giant one-liner? And so to explain how I did that, I have to explain what tensor expressions even are. They are implemented, they're expression trees, and I will explain what that is using numbers first. So if you haven't seen this before, you can represent an arithmetic expression of numbers using a tree structure like on the slide, and you can evaluate it from the bottom up. So if we go to the bottom, you can do 8 minus 5 is 3, you can do 3 times 4 is 12, 2 plus 12 is 14, you have your result. And you can imagine doing the same kind of thing but with tensors, and you can imagine doing the same kind of thing with tensors in SpECTRE. And this tree is the exact kind of thing that is created and evaluated when someone writes a tensor expression in SpECTRE. And this is the thing that we want to cut up into smaller pieces, into pieces of size 8, when it's really big, because that's when it's slow. And so to explain how I did that, I will just show a version of that with numbers to make it easier to follow. But in reality, we want to do this with big trees in SpECTRE, 8 operations at a time. So what I did, equivalently with numbers, is I said, okay, if I have a commutative operation like addition at the top, and if the thing on the right of the addition is bigger on the right than on the left, I'm just going to move it to the left. So that is effectively just switching these 2 children. And that's the effect of doing that. The only reason I did this was because it made it easier to think about the subsequent splitting that I needed to do. There was no other reason. So then, okay, so the goal is we want to split this up. Instead of doing this as one line, we want to do it as multiple lines and do it pieces at a time. And so what that can look like is breaking up that one line into 3 lines where you do each operation at a time. But in reality, for tensor expression, we want to do 8. Okay, so back to our problem cases that were horrible. After I implemented the first change, which was if I have a commutative operation with a big thing on the right, I moved it to the left. That sped up the contraction over the 4 indices by 10 times, and it sped up the big dt pi equation by 7 times. And that was just by accident. And then after I split up the tree, using that heuristic of 8 operations, it got both of these equations basically on par with the loop implementation, slightly slower for the second one, and this was a huge victory. And so I don't have time to show all of the benchmarking results. I looked at a lot of inner products, addition, subtraction, mixed products, other big equations, lots of things, but one important result that I want to share with you is one thing I benchmarked is SpECTRE's implementation of the entire generalized harmonic right-hand side. This is a composite of many small equations and large equations, all different kinds of operations. And so what this is kind of a measurement of the overall performance of tensor expressions compared to loops in a real setting in SpECTRE and in a part of the code where we spend a lot of our computational time in our binary black hole simulations. And so this is a very important metric. And so if you look at these results, tensor expressions are doing pretty good. Anything less than 1 means that tensor expressions were faster than the loop and for different sized vectors and different dimensions. So this suggests that they can be competitive in a real setting. And so in conclusion, I'll just say that, yeah, vectors look good. Compile time is something I haven't looked at. So I've looked at it, but it has not been optimized yet. And that needs to be optimized. For very large expressions, the compile time can really go up, and so that needs to be optimized. And I guess I'll just mention that that QR code on the right is a link to all of the benchmarking results in case anyone really wants to see, how the different operations did and such. That's what that link is. So, yeah, thank you for your time.
So we have time for a quick question.
This is really cool. Thank you for sharing. Have you looked into how all your time ups and speed ups depend on the cache size of the processor you're running on?
I haven't. I have had conversations with Niels about this. We have talked about cache size, and something that of primary importance that I want to look into in looking at the what's it called, like the metrics of these runs is I want to look at cache misses in particular, and like for the different level caches. Sometimes we'll see something that almost looks like we've saturated the L1 and then the L2, and there's these kind of these linear increases. And so I do want to look at cache misses. That's one of the first things I want to look at. So we've discussed it.
Let's thank our speaker again.